Thank you very much. Thank you for attending my presentation. I am Gaurav Chobe. I am a PhD candidate at Purdue University. I am working with Professor Akanshu Sharma. The topic of my presentation is performance of anchorages under predominant moment loading, mainly an experimental investigation. Let's consider a steel column connected to concrete foundation with the help of headed studs. Let's consider the embedment depth of the headed studs as H effective. Under the application of bending moment, we will have a tension and a compression couple generated in the system. Let's consider the distance between tension and compression as Z, which is, let's say, the internal lever arm. If we assume that the tension anchor is not going to fail in steel failure, then mostly it is going to fail under concrete cone failure. And the compression on the other side is going to be transferred in the foundation with the help of the compression field. So now the compression field from the base plate will suppress the formation of concrete cone, and that will lead to an increased capacity of the tension anchors. This increment in the capacity is generally represented by the factor psi mn in the Eurocode, which is given by the formula 2 minus z over 1.5 H effective. It is to be noted that the factor psi mn is currently only valid for the case of pure concrete cone failure. Also, in the upcoming ACI 31825, this psi mn factor is included, and it is also similarly, according to the Eurocode, it is 2 minus z over 1.5 H effective. Instead of calling it psi mn, it is basically referred to as psi cmn in this case. It is important to note that the positive influence of the base plate compression will not be applicable if the breakout strength is influenced by the concrete edges. So it means that when the anchor group is close to an edge, we will have a limited breakout available for the concrete, for the anchor, and that will not lead to any increment in the capacity. In light of this, there are some open questions. So is this factor psi cmn valid for the case of combined pull-out and concrete cone failure, which is a predominant failure mode if we are talking about the bonded anchors? This failure mode is characterized by bond failure for some part of the length and concrete failure for the rest of the part. So we would like to understand if this factor is also valid for this particular case. Also, when we have an anchor group located close to an edge, is this factor valid, particularly in case of CC plus PO failure mode and in case of concrete cone failure mode? To answer these questions, we developed our experimental program, and we wanted to target the failure mode of combined concrete cone and pull-out when we do not have any nearby influencing edge. So we tested a 2x2 group of bonded anchors. Basically, the dimensions in this case were the 1-inch diameter of the anchor, 10-inch embedment depth, and the spacing between the anchors in both the directions as 8 inches. So two cases were considered. One where we do not have any edge influence. Basically, the CA min according to ACI will be greater than 1.5 H effective. And in the second case, we have an anchor close to an edge where we have set the value of CA min as 0.5 H effective. And again, in this case, two parameters will be considered if we have loading away from the edge and we have loading towards the edge. So overall, we tested 3 specimens, and the experimental setup with all the instrumentation is shown here. We used several instruments like string potentiometers to measure the deflection of the column in the plane of application of the load. We used inclinometers to measure the rotation in that plane. Then we have strain gauges to measure the maximum strains occurring in the column. We have linear potentiometers to measure the deformation of the surface of concrete upon the concrete breakout failure. Then we have the load cell in the actuator, which will measure the total load applied on the column, and also the anchor load cells, washer load cells or donut load cells, which measure the tension forces in the anchor. The overall setup is shown on the right side with the different components of the test. It's basically a full-scale test that we performed. The first, basically, when, like I showed the experimental program, the first one is the case where we do not have any edge influence. So the edge distance to the nearest edge is greater than 1.5 H effective. The second case is the edge influence case where we have loading away from the edge. And in the third case, we have loading towards the edge. Here, I would like to discuss the results where we do not have any edge influence. The base moment versus drift diagram can be plotted, and the capacity of this anchor group can be calculated with the help of formulations given in ACI. So if we consider the anchor group, the tension angles will govern the capacity of the anchor group, and we can consider three types of failure mode. The first one is the steel failure, the second one is the concrete cone failure, and the third one is the combined pull-out and concrete cone failure. So considering that the two anchors out of these four anchors will take up the most of the load, all of the load, we have the steel capacity which comes out to be around 236 kips. This is at the mean level, so we can compare it one-to-one with the experiments. Then the concrete cone capacity can be calculated with this formula, where now we can include the factor psi CMN, which is basically, which comes out to be 1.4. Then the capacity under concrete cone failure comes out to be 135 kips, and in the case of pull-out, we get around 114 kips as the capacity. So in these three capacity, the governing one will be the concrete cone and pull-out capacity, and the according to ACI, if we can multiply the value with the internal lever arm, which is basically the distance between the tension and compression couple, where we can then calculate the capacity of the moment capacity of this section as 86 kip feet. But from the experiments, we observed that the peak capacity in this case was observed to be 130 kips. So there is a discrepancy between what is obtained from the ACI and what we observed in the experiment. That discrepancy can be explained with the help of factor psi CMN, which I will come to in the next couple of slides. I would like to explain the results evaluation. So considering that the tension, there are 4 anchors in the group. The 2 anchors on the tension side will take up most of the load, which is also seen in this case. The anchor loads are plotted on the y-axis, and the displacement of the actuator is plotted on the x-axis. So it is observed that until the peak is reached, all the load is being taken up by the tension anchors, and in the post-peak region, we have the compression anchors that may activate after the anchors have failed in the tension area. On the right side, I am plotting the plate displacement profile, which basically shows the thickness of the plate that the base plate that we consider in the experiment was around 2.5 inches. And here we are plotting the displacement of the plate at different displacements and the force that we apply on the actuator, on the column. The distance between tension and, so there were 3 potentiometers, one on the tension side of the plate, one in the middle, and one in the compression side. So at initial levels of the loading, we see that the 3 displacements can be connected in a linear line. So it means that we have a rigid rotation of the base plate. The base plate is not really bending, it is just rotating about an axis. At increased loads, we have increased displacements. And after the failure of the anchor group, we have a sudden jump in the displacement of the plate. And after that, again, it basically increases. It is important to note that in case of, on the side of compression, we have the displacements of the potentiometer less than 0 inches, which indicates that we have the base plate suppressing the, compressing against the concrete surface. The tension and the the tension potentiometer and the middle potentiometer had a distance of 6 inches, so this is basically not to the scale. On the y-axis, we have a different scale. On the x-axis, we have different scale. So to calculate the positive influence of the base plate compression, we have to do the test where we do not have any base plate compression. And for that, we did the tension test on the 1/2 anchor group, which was basically pure tension test. And we obtained a capacity of around 100 kips for this 1/2 anchor group, which again failed in the case of in CC plus pure failure mode. Now we have a column which is loaded horizontally with the help of actuator. The load is, let's say, the applied load is P, and it is applied at the lever arm, external lever arm of H. We have the distance between tension and compression couple as Z. So with the help of basic mechanics, we can calculate the maximum load that is obtained in the anchors. So the psi CMN factor in this case will be the ratio of the tension force in the anchors, which is influenced by the compression, to the tension force in the anchors which are under pure tension. So in this case, the psi CMN factor comes out to be 1.7. Looking at the crack pattern in case of moment loading, where the load is applied in the direction as shown here, we have the breakout body as shown in the figure. So looking at the concrete breakout surface, it has a shallow depth of concrete breakout, And also in case of tension loading, where the load is applied in the vertical direction, we see that the total embedment depth of the breakout is around 5 inches, whereas the total anchor embedment depth was around 10 inches, which clearly states that we have pull-out plus concrete cone breakout in both of the cases, and we can infer that the positive influence of the base plate compression is applicable where we have a CC plus PO type of failure. Now this anchor group was moved close to the edge, where the edge distance was to the nearest anchor was 0.5 times the embedment depth, and the loading was applied towards the edge. So in this case, comparing the results to the case where we do not have any edge influence, we can plot the graph, and we observe that the peak capacity was around 70 cube feet in this case, and which is around less than 40% less than the case where we do not have any edge influence. Again, in this case, we can calculate the capacity according to the ACI formulations, where we have the steel strength, which basically remains unchanged because the two anchors, tension anchors, will take up the load. Then we have the concrete cone capacity. Now, in this case, because there is a nearby edge present, the psi Cmn factor will be equal to 1, which will result in the concrete capacity as shown here. And then we have pull-out plus concrete cone breakout capacity, which comes out to be 94 kips. In this case, even though the least of these three values is the concrete cone breakout capacity, we observed that in the experiments we obtained a combined concrete cone and pull-out failure capacity. So the moment as obtained from the ACI is around 56 kip feet, but in experiments we obtained around 70, which again shows that there is a discrepancy between what is obtained from ACI and what we obtained from the experiment. In this case, after calculating the pure tension capacity of 1/2 anchor group, we found out that the psi Cmn factor is around 1.4. So even when there is an edge present nearby, we get a positive influence of the base plate compression. Now in the third case, we have the edge at the distance of 0.5 H effective, but now the loading is applied away from the edge. Again, plotting the graphs on the moment versus drift diagram, we can see that in case of the loading away from the edge, we get a peak capacity of around 60 kip feet, which is around 45% less than the case where we do not have any edge influence. Now, in this case, it is important to understand that when we apply the load away from the edge, the cracks will run from the concrete, from the anchor towards the concrete edge, which will basically result in a concrete cone failure, which is the governing failure mode here. So in this case, the capacity, again, we can calculate from the ACI formulations, and what we obtain in this case is that, again, there is a discrepancy between what is calculated from ACI formulations and what is obtained from the experiments. So in the experiments, we also found that we had a concrete cone breakout, and from that, the psi Cmn factor comes out to be around 1.83, whereas the codes will give a factor of 1.0 in this case. Looking at the crack pattern in both the moment loading as well as tension loading case, in this case, the depth of the concrete breakout extends up to 10 inches from the surface of concrete, and in case of moment loading, in case of tension loading, we also have an embedment depth of like the surface, embedment depth from the surface as 10 inches, which means that it is almost equal to the embedment depth of the anchor, and we have concrete cone failure in both the cases, which we can infer that the positive influence of base plate compression is also applicable where we have an edge distance less than 1.5 times the embedment depth. These three experimental results can be plotted in a graph where we have a normalized base moment versus drift, and it is interesting to observe that the capacity when we have an closed edge is almost equal. This can be explained when we have loading away from the edge, the volume of concrete available for breakout decreases, but the positive influence of the base plate compression is significant. In the case where we have loading towards the edge, we have reverse of this case when we have, then in that case we have more volume of concrete available for the breakout, but the positive influence of the compression is not so significant. It is disrupted by the presence of nearby edge. To understand the crack pattern and the base plate compression in detail, we conducted some finite element studies where we use the finite element software MASA, which is basically the microscopic space analysis developed by Professor Oswald at University of Stuttgart. It uses the microplane model for concrete, and we try to model the loading conditions as well as the boundary conditions as closely related to the experiments as possible. The finite element model was validated for the case of moment loading, where it shows pretty good relation between the peak capacities and also the crack pattern. Also, it was validated for the case of tension loading. And in both the cases, the finite element model is really helpful to cut a section and then to understand how the cracks are propagating. So at peak load, in both the cases, we see that we have combined pull-out and concrete cone type cracks, which again further corroborates the experimental observation that we had. Also, the FEM is really helpful to understand the compressive stresses. So as we know, like when we apply moment load, there will be a compression generated below the base plate, which is also, again, observed from the finite element simulations here. These compression stresses will travel from the point of compression to the end of the anchorage until here, which is basically the end of the tie. In the experiments, we also used something called as pressure-sensitive films below the base plate. So when you apply a moment load, the pressure-sensitive films will change the color, and upon post-processing, we can read the values off of the chart that is given here, which now, when the load is applied in this direction, we found out that the maximum pressure was around 43 KSI in this case. Also, in the finite element model, we observed that when we apply a bending moment, we have around 300 megapascal stress below the base plate, which corresponds to around 43, 44 KSI of the pressure. Of course, there are some regions where the base plate is going to uplift and there will not be any pressure, which is again also seen from the finite element simulation. So overall, we have a finite element model which we have validated with the experiments, and that will be later used to perform some parametric studies, which will include the variation of base plate thickness, the variation of concrete material properties, and the configuration of the anchors. In summary, it is shown that the positive influence of the base plate compression is seen to be valid for monotonically loaded anchor groups, which are failing under combined pull-out and concrete cone failure mode. Also, it is shown that this influence is applicable when we have an anchor group located near the edge, which is either loaded monotonically towards the edge or away from the edge. Thank you.